Roughly 6 miles above your head, there's a river of air racing around the planet at speeds that can top 400 kilometers per hour. And right now, that river is behaving in a way that has genuinely rattled the scientists who study it. It's splitting apart, looping back on itself, freezing in place for weeks at a time. One climate scientist looked at recent satellite imagery of it and said he was honestly at a loss for words to even describe what he was seeing. This is the jet stream, the invisible current that quietly dictates almost everything about the weather you experience, and scientists cannot look away from what it's doing right now. By the end of this video, you will understand exactly what the jet stream is, why it's acting so strangely, and why researchers are watching it with a mixture of fascination and genuine concern. Let's start with the basics, because understanding what the jet stream normally does makes its current behavior far more unsettling. The polar jet stream is a high-altitude air current flowing at elevations between roughly 5 and 9 miles above the surface that moves at extremely high speeds across the Northern Hemisphere. Its fundamental job is simple. It separates cold, Arctic air to the north from warmer air to the south. Under normal conditions, it follows a relatively straight, predictable path, generally flowing eastward across the middle latitudes of the planet. That predictability is exactly what has allowed meteorologists to forecast weather with reasonable confidence for decades. South and generally weaker in its influence on day-to-day weather across North America and Europe. Together, these two powerful currents have historically kept broader weather patterns, anchored in roughly the same places year after year, giving forecasters a dependable framework to build seasonal outlooks around. When both currents behave predictably, meteorologists can reasonably anticipate where storm tracks will run, where cold air will pool, and where warm, dry conditions are likely to settle in for an extended stretch. But according to atmospheric scientists, that predictability has been eroding. For several decades now, the jet stream has been slowing down and losing its shape. Its once subtle undulations, the gentle waves it naturally makes as it flows around the globe, have become increasingly pronounced. These exaggerated waves form massive loops that can trap cold air when they dip southward, or trap warm air when they surge northward, sometimes locking either extreme in place over the same region for days or even weeks at a time. Meteorologists refer to this phenomenon as blocking, and it's the underlying reason so many recent extreme weather events have felt less like a passing few days of unusual weather and more like a prolonged, stubborn pattern that simply refuses to move. A jet stream that flows in a relatively straight line, pushes weather systems along steadily, giving any given region only a few days of a particular condition before something new arrives to replace it. A jet stream locked into a deep, wide loop does the opposite, effectively pinning a high or low pressure system directly over one location for an extended stretch, whether that means baking a region under relentless heat or burying it under repeated rounds of the same storm system. The scale of this unusual behavior became impossible to ignore during one particularly extreme stretch of North American weather, when the southern branch of the jet stream over the continent completely fragmented, breaking apart entirely rather than maintaining its normal continuous flow. This fragmented section became trapped in what scientists described as a vicious, tightly wound revolution, essentially spinning in place rather than progressing steadily eastward the way jet stream waves normally do. That trapped spinning configuration ended up fueling an extraordinarily intense heat dome, one so extreme that even veteran meteorologists were visibly astonished by what they were seeing on their models. The reactions from scientists watching this unfold were striking in their own right. One local television chief meteorologist described the configuration using a single word, insane, adding that it appeared to be enhanced by climate-driven heating and was fueling a record heat dome so extreme that even experts found themselves astonished. Climate scientist Michael Mann, who has spent years studying exactly this kind of planetary wave behavior, responded that he was honestly at a loss to even characterize the large-scale wave pattern he was observing, calling it one of the most disjointed configurations he had encountered in his research. If this kind of breakdown is useful to you, take a second to hit that like button. It genuinely helps this channel keep bringing you science stories that explain exactly what's happening in the atmosphere above us. So, what's actually driving this increasingly erratic behavior? The leading scientific explanation centers on the Arctic. Jennifer Francis, a researcher who has studied this connection extensively, points out that the jet stream exists specifically because of the temperature difference between the equator and the North Pole, a gradient that powers its flow the same way a pressure difference drives wind between a high and low pressure system. As the globe warms, the Arctic is heating at a dramatically faster rate than the rest of the planet, a phenomenon scientists call Arctic amplification. That disproportionate warming chips away at the very temperature gradient that gives the jet stream its structure and strength in the first place. According to Francis, if this weakening gradient turns out to be the true driver behind the jet stream's increasingly wild swings, the implications extend well beyond a single strange weather event. She's explained that this kind of atmospheric instability could make drought, heat waves, and flooding caused by prolonged rainfall all significantly more likely across the Northern Hemisphere going forward. In other words, a wobblier jet stream doesn't just mean more unusual-looking weather maps. It means the extreme events themselves may become both more frequent and more severe as this pattern continues. The mechanism behind Arctic amplification itself comes down largely to melting sea ice. Bright, reflective ice normally bounces a significant portion of incoming sunlight back into space, keeping the Arctic relatively cool even during its summer months. As that ice melts and exposes darker ocean water underneath, the region absorbs far more solar energy than it used to, creating a feedback loop where warming leads to more melting, which leads to even more warming. This effect is a major reason the Arctic has been warming several times faster than the global average in recent decades, steadily eroding exactly the kind of temperature contrast the jet stream depends on to maintain its strength and structure. There's supporting research that reinforces this concern. A study published in the journal Nature Communications in June of 2023 found a measurable correlation between the loss of Arctic sea ice and jet stream oscillations across the period from 1979 to 2022. Snow and ice cover at the poles has a well-documented influence on broader atmospheric behavior, reflecting sunlight back into space and helping maintain the temperature contrast that keeps global wind patterns organized. If Arctic ice continues melting at its current pace, researchers project the jet stream is likely to become even more unstable, with its waves growing larger, particularly during winter months, leading to stronger, longer-lasting weather blocks and more frequent, more abrupt weather reversals. Now, in the interest of giving you the full picture, it's worth noting that this isn't an area where every scientist agrees completely. A separate study conducted at Dartmouth and published in AGU Advances challenged the assumption that climate change is solely responsible for the jet stream's erratic wintertime behavior. That research, led by Jacob Chelef alongside Professor Erik Osterberg, found that the jet stream appears to have gone through natural, if sporadic, periods of waviness even before the effects of climate change became significant, suggesting some of this volatility may simply be a part of the system's natural variability rather than purely a modern phenomenon. To reach that conclusion, the Dartmouth team turned to ice cores rather than relying solely on modern satellite records, which only stretch back a few decades. Ice cores preserve a detailed chemical record of past atmospheric conditions stretching back centuries, allowing researchers to reconstruct jet stream behavior long before industrial greenhouse gas emissions became significant. That longer historical baseline is exactly what allowed the team to identify earlier periods of pronounced waviness, evidence suggesting the jet stream has always had a tendency toward this kind of erratic behavior under the right conditions, rather than this being an entirely unprecedented development unique to the modern era. Osterberg has said these findings genuinely shifted how he approaches the broader problem, pointing researchers instead toward other, more direct links between global warming and severe weather, such as the well-established fact that a warmer atmosphere holds significantly more moisture, which on its own is enough to fuel bigger, more intense storms, regardless of exactly how wavy the jet stream itself becomes in any given season. Before you go, make sure you're subscribed to this channel, because we break down exactly what's happening in the atmosphere above us every single week, cutting through the noise to explain the actual science behind the headlines. Regardless of exactly how much of this erratic behavior traces back to climate change versus natural variability, the practical, on-the-ground effects have been showing up across North America with striking regularity. A wide range of unusual weather events, catastrophic. Flooding in Colorado, a heat wave stretching into Alaska, and bitter cold gripping Florida have all been traced back to the same underlying culprit, unusually erratic behavior from the polar jet stream. That normally direct current, which typically passes over North America somewhere near Seattle, has instead been swinging wildly, dipping dramatically, north and south in a pattern that resembles a volatile line graph rather than the smooth, predictable curve meteorologists are used to working with. At times, it has even split into two separate streams entirely, further complicating forecasts across the continent. More recent observations have added another layer to this story. Meteorologists tracking dangerous wildfire conditions have noted an unusually strong jet stream roaring southwestward directly over Southern California, feeding additional energy directly into the surface-level Santa Ana winds that fan wildfire danger across the region. Scientists describe this as an unusual configuration, given how amplified the upper-level jet stream pattern has become, even though the general timing of Santa Ana wind. Season itself wasn't unusual, illustrating just how directly this high-altitude river of air can reach down and intensify dangerous conditions happening at ground level. At the center of everything scientists are watching right now is a fundamental atmospheric system behaving in ways that don't match the decades of historical patterns researchers have relied on to forecast weather. Whether the primary driver turns out to be Arctic warming, natural variability, or some combination the science hasn't fully untangled yet, one thing researchers across multiple institutions agree on is this: the jet stream isn't behaving the way it used to, and that shift is already showing up in the form of stronger heat domes, more persistent cold snaps, and increasingly abrupt swings between weather extremes. Scientists cannot look away from it, because in many ways, this invisible river, 6 miles above our heads, has become one of the clearest signals we have that something in the system is genuinely changing. For everyday viewers trying to make sense of increasingly unpredictable seasons, the practical takeaway isn't necessarily alarm, but attentiveness. Forecasts issued more than a week or two in advance carry more uncertainty than they used to, precisely because the jet stream itself has become harder to model reliably that far out. Meteorologists across multiple networks have started incorporating more explicit language about blocking patterns and jet stream configuration into their day-to-day forecasts, a subtle but telling sign that this once obscure atmospheric detail has become central to understanding why the weather outside your window increasingly refuses to follow the script it used to.